Thank you, Angus, for the introduction. I'm an honor student from Monash University, and what I'm going to talk about today is my current work with my honor supervisor, Professor Nick Wermuth, on the asymptotic enumeration of bipartite graphs with a specified degree sequence. And I'd like to start by saying a bit about the background. So in the past two decades, various attempts have been made to verify an asymptotic formula for the number of labeled graphs. And this problem was completely resolved by Lebenau and Wermuth in 2017. For the bipartite case, however, there are still some significant gaps remaining. And some of the gaps were filled by Lebenau and Wermuth using the similar proof strategies. And in my current work, we are adopting the same proof structure with some modifications. And this allows us to further extend the range of degree sequences covered by the asymptotic formula for bipartite graphs. And here's the conjectured asymptotic formula in the bipartite case. And so I'd like to first take you through the notation. So it's just a very standard ones. We'll let S and T denote the two sides of the bipartite graph, and the cardinalities of S and T are L and N respectively, and denote the degree sequence by D, and the number of edges by M. And we also define, also denote the average degrees by S and T. And here the density mu is a very important parameter, which we'll revisit quite a few times in the next few slides. And finally, we define variances for both sides of the bipartite graph in the standard way. And now the asymptotic formula. So we assume some regularity condition here, namely that the degrees of all vertices cannot deviate from the average degree by too much. And we call such degree sequences typical degree sequences. And the asymptotic formula is as follows, where the HD here is the correction factor. And now let me just talk to you about the setup for the proof structure. So we denote by G the uniform probability space of labeled bipartite graphs. And so the cardinality of this space is going to be L times N choose M. And we denote by D the space of degree sequences induced by the space G. And finally, we denote by B this binomial space, where every element is a random vector of length L plus N, where the first L elements, or the first L entries and the last N entries will follow binomial distribution with different parameters, and they're all independent. And this whole space is conditioned on this condition here. And if any sequence satisfies this condition here, we then say that this sequence, be it a degree sequence or not, is balanced. And with just a little effort, we can show that given a balanced sequence, its probability in this binomial space is going to be this expression here. And we can already see that this looks very similar to what we have for the conjectured asymptotic formula. And here's what's proved by Lebenau and Wermuth in the recent work. And here we can see that the main condition is this one here. And this is already very good improvement from previous results, because previously, except for the very sparse regime, this formula was only proved when the cardinalities of the two sides are within a multiplicative logarithmic factor of each other. And in our current work, we're able to further extend this condition to around at least L equals N squared, or N equals L squared. And here we have an asymptotic formula for the probabilities in the two spaces. And so if we multiply both sides by the cardinality of the space G, then it's going to give us exactly the desired asymptotic formula. And so now, instead of introducing the modification, I'll discuss the key pieces of the argument first, which will be very similar with or without the modification. So we first introduce some ratios. So we let this NFD denote the number of bipartite graphs with degree sequence D that contain the edges in the set F. And we define these three ratios here based on this, this N. And we note that because we're dealing with a binomial space, because we're dealing with a uniform distribution, we can regard these three ratios here as probabilities in some sense. For example, the P and Y here can be regarded as the probabilities that a bipartite graph satisfying the degree sequence D contains the edge AV with the edges AV and BV. And the ratio R is actually the most important of the three, and it can be seen as the ratios of probabilities of adjacent degree sequences. And we can then derive a system of recurrence relations for these three ratios. And the idea about how to use these recurrence relations is actually very simple. So we just plug in an initial estimate for any of the three ratios. And it can be very crude. It doesn't really matter, because it can be shown that after each round of iteration, we can gain a multiplicative factor of mu, in the sense that the error term will be multiplied by mu after each round. And so we can already see that for very small mu, say mu in the very sparse regime, we only need to run this recurrence a finite number of times in order to arrive at a very accurate estimate for all of the three ratios. However, for large mu, say mu in the constant regime, we'll need to run this recurrence an infinite number of times. And in this case, in order to make the argument more rigorous, we need to define a set of operators based on the recurrence relations. But the essential idea is still the same. And we now introduce a probability theorem, which, coupled with the estimates for the three ratios, can give us the desired asymptotic formula. So what this probability theorem is saying is basically that for some underlying set omega, if a graph has its vertex set being a large subset of omega, and the edge structure such that the ratios of probabilities of adjacent vertices in the two spaces are uniformly close to each other, then we can approximate the probabilities in one of the spaces with the probabilities in the other. And here's how to apply the theorem. So clearly we'd want to define the underlying set omega to be the set of all balanced degree sequences with length L plus n. And also it's very clear that we'd want one of the spaces A and B to be the space D of degree sequences, which we defined before. And it can also be shown that with high probability, the variances of both sides can be bounded by twice their average degree, hence the construction of the subset E. And for B, we can see that the probabilities in this space are just the probabilities in the binomial space defined before, multiplied by the correction factor H. And finally, for the graph G, whose vertices are the degree sequences, we let two vertices, or should I say two degree sequences, be connected if either of these two conditions are satisfied. And we can already see the connection between this construction and the ratios before, because if we denote by D, denote this by D, then we have V1 equals D minus EA and V2 equals D minus EB. And so this ratio here becomes the ratio of probabilities of adjacent degree sequences. And that's exactly how we define the ratio R. And because we have already obtained some very good estimate for the ratios, the conditions of this probability theorem can be satisfied, and thus yield the desired asymptotic formula for the probabilities in these two spaces. And finally, I like to wrap things up by introducing the modification we've done. So we now redefine the three spaces G, D, and B. So and the core idea is to fix the degree sequence of one side. So for example, if we fix the T side, then we define GT to be the uniform probability space of all labeled bipartite graph with M edges, n degree sequence T. And so in this case, the cardinality is going to be this product here. And we define D to be the space of degree sequences induced by G, induced by GT, yeah, GT and DT. And the difference between this binomial space BT and the original binomial space is that the last n elements will no longer follow a binomial distribution. Instead, we just set them to be the same as the degree sequence T. And so in this case, under the new construction, if we're given a balanced sequence, then the probability of it in this new binomial space will be this. And here we can already see that if we multiply it by the cardinality of the space G, it'll give us exactly the main term in the desired asymptotic formula. And the benefit of this new construction is that we can have a better approximation between the probability ratio in the two spaces, so namely a smaller delta. And so we're able to accommodate a larger R if we want this to be of order little o of 1. And with little effort, it can be shown that this R is of order big O of this. And so a larger R directly corresponds to an extended range of degree sequences covered by the asymptotic formula. And that's it. Thank you for listening.
Let's thank Hongyi for giving a great talk. All right, are there any questions from the audience?
I have one question.
Go.
So,
yep.
Does your result for every density, or I mean, for sparse and dense, does it hold for all the case, or?
Yeah, not necessarily. So let me go back to the statement of the theorem. So in the statement, so for this theorem, what Lebanon and Wehrmont proved was that for sufficiently small constant mu0, and for all densities below this constant, we can and for cardinalities satisfying this condition, the asymptotic formula is going to hold. So it's sort of doesn't really cover all density ranges, but it still covers quite a lot of density ranges. Yeah, up to a small constant. Yeah.
So here, second condition about the L and N means that each part has size almost similar, right?
Yeah, in some sense, because yeah, L and N just the cardinalities of the two sides. Yeah, but previously, sorry, you're good. You go first. Yeah.
So what is obstacle to analyze of the case of the when graph is dense?
Yeah, this is not really a very rigorous term, I'd say. So so to be more specific, I'd say, so previously the results, so usually when we say sparse, we actually mean of order little o of 1. And but previously it was actually only proved for density of order little o of 1 over L times N to the a quarter, which is much smaller than little o of 1. Yeah, and except for that very sparse regime, this formula was only proved, like I said, when the cardinalities of the two sides are within a multiplicative logarithmic factor of each other. So this is already some very good improvement. Yeah.
Thank you.
Is there one quick question left, maybe? All right, well, if not, let's thank the speaker again.